Hi, this is Kumar Shukla from Perpetual Learning. Today I will show you the what is the power semiconductor devices and what kind of power semiconductor devices today we have, today is available. And this is lecture 2 of the power electronics. So the power, what is the power semiconductor devices? Actually, if you look into the history, then from 1900 to till now, in 2021, you can see there are so many kind of semiconductor devices involved, like thyristor, GTO, GTR, and ICT, IGBT, IGBT, power MOSFET, etc. So this has involved in different phases: first phase, second phase, and third phase. And now this recently going on. And in the previous lectures, I have mentioned the gallium nitride device and silicon carbide devices also, because the coming future is totally based on the silicon carbide and gallium nitride kind of devices, because they have extremely, they are a very good candidate for the power electronics converter. So let me show you the first question, the classification of the power electronic devices. So basically in power electronics, there are three kind of devices is involved. The first one is an uncontrolled device. What is an uncontrolled device? You cannot be apply the gate control signal like diode. Okay, you cannot be control the current from this one or this one. You have just applied the voltage plus minus or minus plus, and the current will flow according to, sorry, this plus, this is minus. Okay, accordingly, suppose if you are applying the plus and minus, then current will flow, and if you are applying the plus here and minus here, then current will not be flow. So okay, so now in the half control devices, thyristor, so in this fashion, you can only turn on by the gate current signal. Okay, you can turn on this device using of gate current signal, suppose here. And for the turning off, if you just apply the gate current for the turning off, if you have just removed the gate current, then also at that situation, this thyristor will not be turned off. So to turn off these devices, you need to be force commutation method and line commutation method. There are different commutation method involved. What is the commutation? That means you have to be turn off the device. Okay, so anyway, so the thyristor is an uncontrolled device, half controlled device, because you can turn on this device, but you cannot be turn off the device. Now the fully controlled device, this one. Now the fully controlled device, you can turn on the device using of the gate voltage. What is the gate voltage is applying here, and if you remove it from this device, suppose this is the MOSFET, and suppose if you are applying the gate and source here voltage, till that MOSFET will be turning on, MOSFET will be conducting. If you remove the gate to source voltage, then MOSFET will not be conduct. So this is a fully controlled device. You can turn on the device, you can turn off the device. In the half controlled device, you can only turn on the device, or either you can turn on the device, or you can turn off the device, but usually turn on is involved here. So in a half controlled device, in uncontrolled devices, you cannot be turn on the device, you cannot be turn off the device. So to turn on the device, you need to be apply the external biasing circuit. Okay, so now what is a VI characteristic and switching characteristics of the power diode? Okay, so one more important point, what is the difference between the signal diode and power diode? Okay, so in the signal diode, the rating of the signal diode is very low compared to the power diode. And in the signal diode, there are two layers. There are two layers, P plus and N plus only. There are no, P plus or N. Sorry, P plus or N. So what is the meaning of P plus? If I'm talking about the P and N is more only. So their doping level is near to 10 to power 17 or 18, 10 to power 17 or 18. If I am talking about the P plus and N plus, then the doping level is very high, like 10 to power 19. And if I'm talking about P minus or N minus, then the doping level is very low, less than 10 per 17. So let's say 14 or 16 kind of thing. So this is the I layer also. This is called the I layer. So usually this power diode is called the pin diode. Okay, and this I layer, why this layer is introducing here. So this layer is responsible to increase the power, to increase the voltage capability, the breakdown voltage capability. Otherwise, in the signal, if you are using the signal diode, let's say this is a signal diode, and this at this signal diode, if you are using the reverse power, reverse voltage at the 50 volts, suppose, then this signal diode may get destroyed. But for the power diode, in the power diode, there are I layer, there are some small doping layer, and this thickness is very small. So what will happen, the depletion range will going to be increased and not touch to the P plus layer and not touch to the N plus layer. And there are some reason, the space charge region can freely if you are applying the reverse bias, and it can be inherent, it can be able to support the higher voltages. So this is a constructional view. This is the symbol of the PN diode. And what is the difference? So yeah, one more important point. In a power diode, there are IGBT characteristics, look here, but there is no leakage current is involved because this I layer is here. Okay, but I mean, if the reverse bias is happening, but in the signal diode, there are some leakage current is in this manner. I mean, will show why, because their power range is low, but there are no I layer, so there are no, I mean, high impedance like kind of thing, I mean, in their path. Okay, so always remember this in signal diode, this line, I mean, this line is happening, this red line showing here in this fashion. But in the power diode, there no leakage, I mean, there leakage, but that is very small, it is very small in manner. Okay, so if you look the ideal characteristic of the device, then this ID versus VD in this fashion, I mean, here and here is showing no, I mean, avalanche breakdown kind of thing will happen in an ideal diode, right? How we can make this ideal characteristic? So let's say this is a diode, you are applying the plus and minus here, so the current will draw. Okay, so suppose this is the ID versus VD characteristic. So I am in, suppose I am in this point. Now if you are applying the minus and plus, then current will not be flow. If you are applying the minus and plus, then obviously no current will flow through the device, I mean through the diode. Then the negative voltage will show in this fashion here. So the curve will be show in this fashion, and the ideal curve can be made the switching characters. Remember, the diode switching characters, there are two interest always be drawn. The first one is the voltage peak whenever the device will going to be turned on is. Okay, and another one is a reverse recovery charge. Okay, so here the one of the character is playing the role, that is a snappiness factor. The snappiness factor is a T5 by T4. T5 is always be unintentionally is come, S is a T5 by T4, right? So you can say the reverse recovery charge the manufacturer is provide, and the TRR is a T5 plus T4. So manufacturer provide the S and TRR. So yeah, so here one more important point, this is the linear characteristic will draw, I mean, in the when the device is going to be turned off. So you can say the di by dt is equal to I I mean the current is here involved here, IRR by what the time is involved here. Okay, so this is called T4. So T4 is here, and TRR by T4 is here. Sorry, this is one of the misleading equation. This is a TRR by T4. So using of this T4, we can replace this one di by dt, because dir by dt depend on the what is the rate of change of current expression. So this is the IRR, and T4 is equal to TRR by S plus 1, like in this manner. Sorry, in this manner. So by changing this equation, between them you can achieve this TRR equation. This equation, square root of 2QRR 1 plus S upon TRR. Here one more important point. What is the QRR here? QRR is nothing but what is the area involved in it, because the current and time area called the charge. Okay, so half what is the area T4. Basically this should be TRR, but T5 is usually less, so T5 is equal to T4. And what is the current? So yeah, and why the one of the important question, why this voltage spike is come, this voltage overshoot is come? Because they always remember, this is not come this will not come in the signal level diode. This will come with the power level diode only. So what is the reason the voltage overshoot? The first one reason is the ohmic resistance of the drift region, and the another one is the inductance involved the silicon wafer. What is the meaning of silicon wafer? You device there metal involved. Okay, so the metal, the metal involved and different things involved, their inductance actually will come into the action, and that inductance of the device, remember I'm talking the inductance of the device, I'm not talking about the inductance of the wire and coil and different things. So the inductance of that device, every device has some inductance, maybe it's very low, maybe very high. So the inductance is very low. So what will happen, that di by dt is very high. Okay, because this di by dt is very high, so what will happen, the voltage involved it this and in this, in this amplitude. Always be careful about it. So that is the reason the snubber for the diode is necessary. So I'm not explaining more detail on the diode characteristic, because this is a very obvious thing. Why on voltage is here, why this one, why this reverse recovery charge is here. So my intention is to show the snappiness factor of that diode, and the overshoot is here, and the third one is the reverse recovery charge. Okay, so let SCR. So the SCR diagram is looking here, in this fashion, and in this SCR, if you look the 1D diagram, then you can say the PN device is here, where the 3 junction involved here. And if you look the VI characteristic of this device, then you can say this is the unstable mode or reverse blocking mode. This is called the reverse blocking mode here, or unstable mode. And this is the forward blocking mode, because the device is still turned off, and this is the still turn on case. So here, if you are not applying the gate current, because here gate current, if you remember that just a previous slide, I have used the term, this is the half control device. You can turn on the device using of this gate current, but you cannot be turn off the device. So if I is equal to 0, then the current wave shape is following in this manner. The following this red signal path, if you are following my cursor, and then again it's move into the holding current, and it will be this anode current will be following the what is the whatever the requirement of the DC static characteristic, and accordingly that will follow the path. So this is called the breakover voltage. When Ig equal to 0, so what is the maximum voltage we will achieve? This is called the breakover voltage, which is not desirable. But if you are reducing the Ig, if you are increasing the Ig from the 0 volt, let's say this one, then this breakover voltage is decreasing, which is very good one, which is very good for us, because manufacturer provide the a limit breakover voltage, let's say 1 kilovolt. So this 1 kilovolt rating, this can achieve if you are decreasing the breakover voltage using of the gate current, then 1 kilovolt rating is still there. So this you can use your device in a safe zone, and then again reducing the gate current, and again reducing the gate current, uh, you can fastly turn on your device of the thyristor. Here two term will come, this IV characteristic. The first one is a holding current and the second one is a latching current. What is a holding current and what is a latching current? So the holding current involved the turning of the case. The current, the minimum current, because holding current and latching current is both of these, these are the current, and these are the anode current. And the holding current, the minimum value of anode current below the current. What current? Below this current, holding current, the thyristor will get turned off. And the similar case, if you are talking the latching current, so turn on process involved it, and the latching current is equal to 2 to 3 times of the holding current. So that means, so latching current, minimum value of anode current which it must attain during turn on process to maintain the conduction when gate signal is removed. What is the meaning of this? Let me more clarify you. If you are applying the gate current, so how much time is needed to apply the gate current? Because no need to turn on or no need to turn off for the thyristor. The only gate current requirement is at a turn on procedure. So at the starting you need to be apply the gate current, higher gate current, because to avoid the power losses, turn on power losses, and then smoothly just provide the gate current till the SCR must turn on. Or you can say the anode current should be greater than the latching current. After this time, you no need to apply the gate pulses and gate current. Obviously, why this anode current? This anode current should be function of this anode current may be function of the device. So no, the answer is no, because let's say you are using the thyristor here, and there are some magnetic inductance involved, and this is the DC voltage. So the current flowing this inductor current, that is obviously equal to the what is the current through the devices, and this is called the anode current. And according to this device characteristic, this thyristor characteristic, that current should be greater than the latching current. And if the anode current fastly greater than the latching current, then you can say your device has turned on fastly. So here usually two BJT model involved, because if you just this one, if in this fashion, if you just remove P2 and this P2, N2, this N1. So you can say, this characteristic I have just, this one, this characteristic I have used in this fashion, P1, N1, and this is the anode, this is the cathode, and this is the gate current involved. Okay, so this is gate current involved, and you can, this PNP transistor, this one, and this NPN transistor in this fashion you can use. So this transistor has, thyristor has two transistor model inside it, this in this construction features. So yeah, so I was talking about this power pulses, I mean, this is the high losses involved in the thyristor only. Okay. So yeah, so before going to ahead, I have to just summarize one more point that the gate current, if you are using in this fashion, so you no need to continuously apply the gate current till the SCR should be on. This is the what is the problem with the dV by dt? So the problem with the dV by dt is nothing but if you yeah, one more important point I have just escaped, so I need to be explained. So yeah, here one more point. In the region of the forward blocking mode, in this point, in the blocking mode, forward blocking mode, J1 is a forward biased. Okay, this junction, and this J3 is a forward bias, but this J2 is a reverse biased. Okay, if you come into the forward on state mode, because forward on state mode and forward blocking mode is a stable mode, so forward on state mode, then this J2 come into the forward bias, then current can flow easily. If this is the reverse bias, then current will not be flow, and in the reverse blocking mode all junctions are getting the forward reverse biased, or maybe one of the junction maybe forward biased. So yeah, so here the important that is the important point. So when J1 J2 J3, I have just used the term J1 J2 J3, and this is reverse bias, sorry, this is the forward biased, this is a forward bias in forward blocking mode, in forward blocking, remember, forward blocking mode. So reverse, in the reverse bias mode, this will draw like a capacitor, and what is the charging current is involved in, sorry for the trying. So what is the charging current involved in, and this charging current is nothing but C into dV by dt. Okay, so they needed the time to sufficiently the carriers involved the J2, I mean, if you are turning off the device and turning off to the turning on the device, then the current, I mean, that charging current is very high. So dV by dt is very high, and that dV by dt again can turn on the device. Because of there are no external biasing, so the current through the device may be going to be zero. High dV by dt, high dV by dt of the I mean, if you are applying the, suppose this is the thyristor, and suppose high dV by dt again I am applying here, but I want to turning off the device. This case will happen in the phase control rectifier time, we will discuss later, but for now, this thyristor, if you are just plus minus Vf is applying here, and the di by dt, or what the current is flowing, sorry, what is the charging current involved in, that charging current is high, because that dV by dt is suddenly changed from reverse voltage to the forward voltage. What is the reverse voltage? I mean, suppose 440 volt is there, so 440 volt plus minus, plus is a Vf, and plus is a Vf, and minus is a minus stand for the reverse voltage. So to limit it, there are manufacturer dataset, some dV by dt rating is available, and we have to be minimize it, that dV by dt rating. So we have to be make a circuit, or we have to make a proper way to limit dV by dt, actual dV by dt of the device, from dV by dt of the rating of the devices. Otherwise the device may again get turned on, and it may disturb the device and may destroy the device. So here's some important points here. Here one of the most important device, that is a GTO, and why GTO is used and why Triac is used. This is a very interesting question. So actually thyristor is an uncontrolled device. To make a fully controlled device, we have introduced the GTO, and we have introduced a Triac. Okay, But GTO has a one drawback, that is they that require a large negative current for the turn of the process. For the turning on, this is okay, but for the turning off, the large negative current is required for the GTO. Okay, this is the basic comparison between the SCR and BJT. And because I have already mentioned, for the SCR only for the turn on time the gate current is required in this fashion: a high gate current, then a small gate current for only turn on period. But for the BJT there are continuously gate current, and continuous gate current is involved, and that means base current. Okay, because symbol of the BJT is here, so what the current is required here, this is called the base current, and this base current, continuous base current, is involved. Voltage and current rating: SCR has high voltage and current rating among the other devices, but BJT has low voltage and current rating. In fact, this has a very small frequency device. Okay, BJT. Surge current capability: SCR has excellent surge current capacity, but BJT is not. In last 4 decades, we have seen that SCR has more reliable, but BJT has a less reliability. And yeah, one more important point: voltage and current rating high and low is depending on the manufacturing also. Okay, so this one question has come in IS 2000. So yeah, the basic difference between the Triac and Thyristor. So Triac, Triac is a bi-directional device, and SCR is a unidirectional device. And if you compare the IV characteristic, then you can reach the characteristic only this one. Okay, in this one, I mean this characteristic only for the SCR. If you are using the Triac, that the symmetrical characteristic you can get here. I mean for Triac characteristic, I mean this completely characteristic, because Triac is nothing but it's a anti-parallel device. I mean this is the suppose thyristor SCR, so only this one and this one, there are two terminal, there are one gate terminal, remember, and there are two terminal, MT2 and MT1. Okay, so yeah, this is the next question: what is an IGBT? Okay, so IGBT usually stand for the insulated gate bipolar transistor, and this is a voltage controlled bipolar device, and there are different names available here. The advantage and disadvantage is here. Please pause the video and see this: what is the advantage and what is the disadvantage. See, one more important point: if you see the construction view, in the IGBT there are parasitic thyristor involved, that if this thyristor will turn on, then this is unintentionally, because this will introduce the latch on or latcher problem in the IGBT. So what is the latch on and latcher problem? Yeah, if a latcher problem will introduce, then what will happen? The IGBT, I mean, because to turn on the IGBT, to turn on the IGBT and to conduct the IGBT, their gate current is involved. Okay, I mean, what gate current I'm talking about? Current. Okay, this gate current is I'm talking about, because IGBT symbol is in this fashion. Okay, remember, this is a gate, this is a collector, this is the emitter. Okay, this is a hybrid version of the MOSFET and MOSFET and BJT. So yeah, so when the IGBT, what the current is flowing, what the current is flowing, I'm applying the gate current to continuously turn on the device. I need to apply the gate current, and to continuously turn on the device, I need to be to turn on the device, this IGBT, I need to be gate current involved. Okay, I need to be gate current applied. Okay, so if the current, what is the current is flowing here, that current is greater than what the manufacturer datasheet provide, like some threshold current, and this threshold current designed by the manufacturer. Okay, if you increase that current through the device greater than this one, then latcher problem may happen. And this latcher problem, if once arise, then you cannot be turn off or you cannot be carry the device. It will carry by in itself, which is not valid, which is not good. So you have to be use the force commutation of the device. Okay. Here, one of the most important point, the buffer layer. Why buffer layer is needed? Please pause the video and just read this statement. I am sure you will get a good answer. Why the buffer layer is required. Another question, how much different the IGBT from the MOSFET? Okay, because there are buffer layer, there are injection layer. The only different, see, if you look the MOSFET characteristic, then their parasitic BJT is involved. Okay, apart from this, that body diode is also involved. Okay, and one of the important point, that P n minus, I mean body region, trip region, and n plus region is there. So which region you have to be introduced the injection layer. Okay, the P plus layer. But why it is here? You can get the answer from this slide. You can realize the devices. Okay, how we can realize the ideal characteristic of the devices. So like what is the IV characteristic of the devices? So you should try in the for the MOSFET, for the IGBT from their characteristic. But for a small we have very small period of time, so I will show you the suppose, I will show you the one device realization, the characteristic wise. Suppose given is a minus plus characteristic, and the voltage, the terminal is a 1 and 1 dash. Okay, and the another one is a given slide, given one is, if I am just control, this is a control device, so I have to be realize the device. Okay, 1 and 1 dash, this is the current. So what is the meaning of it? The meaning of is, suppose the IV characteristic is here, and the plus minus if I applied, okay, no current will flow. So plus, suppose I am using this one VAB, this is a VAB. So suppose this is A, this is B, this is A, this is B, so VAB. So plus can be still here because no current is conduction, and minus can be still here, so no current is conduction. So if the minus is here, so this device is called the reverse conduction capability. Now the current can flow in this direction, so that means this diagram. So I can use this kind of characteristic. Okay, so forget about it. First option is given, the thyristor 1 and 1 dash. So is it true? So let me show you. If you are applying the plus minus and the gate current, okay, so gate current is for the just for the turning on procedure. So IV characteristic is here. So I'm plus minus is applying, and my intention is to turn on the device. Accordingly, I have used the gate current. So yes, the current will conduct. So the voltage across it 0. That means the current can be flow. Okay, here. Now the gate current I have removed. I have removed. That means I am not applying the gate current. So then I am applying the plus minus. Then current will flow? No, obviously not. So plus minus is here. If it is minus and plus, then obviously this minus and plus. So yes, this is matching this characteristic to this characteristic. So first option is correct. If I am giving you second option, this in this fashion, so what will happen? This is 1 and this is 1 dash. So if I am applying the plus and minus, and this is the IV characteristic, and in this plus minus the current cannot be flow in this way, and if I am applying the here current, continuous current, to turn on this BJT, so yes, current can move in this manner. Okay, so yes, current can flow and voltage will be 0. If I am applying the minus and plus, instead of the applying the bias current, then current again can flow in the reverse direction. So here I can achieve this point. Remove the bias current here, and I am applying the plus and minus here, then current cannot be flow in this manner and not through the device. So I have achieved the plus minus here. If I am applying the minus and plus here, then current can flow through the diode here. That means negative direction. So achieve I cannot be match this option to this option. Okay, so the only the first option has third option in this fashion. So let's say if I am using the IV characteristic and I am applying the plus and minus, to turn on the device I am applying the base current. So this device has turned on and plus minus I have achieved. Then current can flow through this device to this diode. So yes, current, this point I can achieve instead of 0 voltage, because the if the device has turned on, then approximately 0 voltage. Okay. If I am using the minus and plus, I am using the minus here and plus here. So the device get reverse biased. Instead of the base current is not equal to 0. That means I am applying the base current. So current cannot be flow. So it has a reverse bias capability. That means I can say the minus here. I can get this point. If I have removed the base current here, then no conduction can form because BJT has turned off. So if I am use the plus minus here or minus plus here, doesn't matter because current will not be flow. So I can reach this point also. So that means this portion and this portion I can achieve. So option 1 and option 3 I can get for this kind of arrangement. I will show you the some other examples in the next lectures. I have some doubt and you have some suggestion, you can send me using of my mail what I have shown in my first slide.